Our next paper is entitled Ground Penetrating Abilities of Broadband Pulsed Radar in the 1 to 70 megahertz range. And our speaker is Kees van den Doel.
Thank you. Thanks for coming. So I'll be describing some experiments, and the goal of the experiments is to figure out how radar waves propagate through rock, specifically limestone. So as everybody knows, ground-penetrating radar is a very cheap, non-destructive and attractive technology for mapping subsurface structures, but it's limited to shallow depths. The reason for this is that the frequency range in use in normal applications is between 10 and 100 megahertz or even higher. And those frequencies attenuate rapidly in Earth, so that limits the penetration depth. However, there are a couple of low-frequency pulsed radar systems in use, which use a pulse with center frequency in the 1 to 5 megahertz range. And with those systems, you can map the subsurface up to several kilometers down, but only in rather exotic environments, most notably on Mars from orbit and on the Antarctica ice shelf. So the question I'm addressing here is, how far could we actually see on Earth, except on Antarctica, besides Antarctica, with such a system? So to test this out, we performed some experiments, and we used a radar system manufactured by Adrok. It is a radar pulse which has a low frequency component, actually at 3 megahertz, as well as high frequency components. And we test this system out underground in the currently inactive zinc mine in Pandoray in Washington. And we sent our pulse through various layers of limestone and try to figure out what's happening to it and how far it penetrates. So we'll perform two types of experiments, transillumination mode and reflection mode. I'll be mostly talking about the first. So transillumination means you send a wave in from one side and you measure what, if anything, comes out on the other side. Then you change the thickness of your rock slab and you see how everything changes. And this way you can obtain a measure of attenuation, or you can even try to make the rock thicker and thicker until you don't see anything anymore. Problem is that we're looking at ranges of 100 meters or more, so it's not so easy to find such layers of rock. Second experiment I'll describe is a reflection mode experiment. It's more a feasibility test. We'll try to send a radar pulse through 350 meters of rock through a known water body and see if we can measure a reflection. So the transillumination experiment is designed to give us a number of handles on propagation. First of all, there is attenuation, and we'll measure that in terms of skin depth. So skin depth is the path length after which the amplitude decays by a factor of 1 over E. Radar people like to use decibel per meter, but we'll use skin depth here. Second thing we can measure is the dielectric constant. That's just directly related to the velocity. So it's pretty easy. You just measure how long it takes for the pulse to travel through and divide by the travel time. Then we want to find ballpark physical parameters for the ground. And so we're looking at typically resistivity and perhaps polarization loss parameters. To do this, we have a Maxwell model that we implemented in a finite volume discretized time-stepping simulation to create synthetic data, and then we try to adjust the parameters to match what we measure to get ballpark material parameters. So I'll give you the results, or rather the interpretation of our results straight off, and I'll go into details later. What we believe we observe is that the skin depth is about 4 meters close to the walls in the limestone pillar, but it increases up to 150 meters in the interior. The dielectric constant, the relative dielectric, is about 18 close to the walls, and it drops to 6, which is characteristic of dry limestone in the interior. So clearly there's some moisture effects going on. In terms of an interpretation within the Maxwell model, the resistivity parameters corresponding to this would be roughly 300 ohm meter close to the walls, but dropping down to 12 kilo ohm meter in the interior. And it appears that the high frequency losses are due to polarization losses and the low frequency losses due to conductivity. So before we can interpret what comes out, we have to know what comes in. So we'll start off with actually measuring what comes out of the equipment in air, and it's depicted in this graph. So it's a rather long and complicated beast, this pulse, and it has multiple center frequencies at 3, 20, 30, and between 55 and 70 megahertz. And the design rationale for this is that the low frequency part will allow deeper penetration, whereas the high frequency part is it gives you increased resolution for shallow imaging. And the other plot is the power spectral density showing the complicated spectral content of this animal. So this pulse will travel from right to left through air and goes in the rock and then comes out on the other side. Here's the experimental site, or rather a sketch of it. All the gray stuff are tunnels and everything else is limestone. This is about 600 meters underground in Van Rey mine in Washington. And we sent the pulse through the limestone in the 5 paths with increasing length indicated here. So the transmitter is sitting at the big red arrows. We placed the receiver interactively at these blue arrows. That means we had an array of about 20 locations where we measured the return and we picked the strongest reflection, the strongest signal. The reason is that the signal emitted from the antenna is directional, and so you can think of it as a beam that's aimed at the opposing wall, and we try to find the center. This also guards against surface waves that could travel this way and could fool us into thinking we're going through limestone. If that would happen, the amplitude should increase if we come closer to the source here. And and finally we replicated the whole setup in air to make sure there are no equipment glitches that we could mistake for data. Here are the raw results from 15 meters down to 120 meters penetration from top to bottom. So the obvious thing we can extract from this is that the pulse arrives later the longer it travels, so that gives us the velocity and thereby dielectric. The amplitude changes, so that should allow us to estimate skin depth. Also the shape changes, so that's a frequency dependent effect, and that's a little harder to get at. So it cannot be caused purely by conductivity losses, because at least in the simple Maxwell model, the frequency losses are conductivity independent. So we'll consider polarization losses to explain this, or rather put a number on this. So in this plot, we'll show the amplitude of what comes out as a function of how far it has traveled, as well as the inferred dielectric reconstructed from the velocity. So if we know the amplitude at 2 different path lengths, from the difference we can compute the skin depth. So I've indicated the skin depth that we inferred on the plot on the top left. And I've skipped over path 3 for a reason I'll explain in one moment. I'm ignoring that. So we get a skin depth that drops from, goes up from 4 meters to 30 meters. Well, 31 is a little bit optimistic. 30. These are ballpark figures, not very accurate, I think. All the way up to 150 meters. And the dielectric starts out quite high, almost 18, and then goes down for the longest travel path to about 6, which is characteristic of dry limestone. So the only thing that, so it's all limestone, so the only thing that really changes is the moisture content. So this clearly indicates that the short paths go through wetter limestone than the long paths. This is also entirely consistent with this, with these skin depths, because of course moisture, more moisture means more conductivity, lower resistivity, and higher losses. So why is path 3 doesn't fit? Well, I think we didn't design the experiment quite right, but it gives us an additional clue that the explanation I came up with to explain this is correct. Because I think what's happening is that around the walls there's a diffuse layer of moisture that comes from the walls and penetrates into the limestone, but the interior is dry. So all these paths are relatively clean. They see a absorptive layer here with high moisture and one here, but the rest propagates through dry limestone. But this path 3, it passes through this cavity here, so there will be additional moisture in the middle of the path, thereby dropping the amplitude, so it doesn't fit. What we really want to do is vary only one parameter, the length, and keep the material the same, so that was not true for path 3. Okay, now how can we translate this into conductivity or resistivity? So we have to have some sort of a model. So our forward model is Maxwell equations coupled to a ground model, and the ground model incorporates conductivity as well as polarization losses. And we use the Debye model, which is characterized by a single relaxation time. It's not a very realistic model, but we're after ballpark figures rather than accurate modeling. So I've written down the equations here. So E is the electrical field. The first and the last term are Maxwell's equation in a vacuum. This term here is the polarization term, and the polarization is determined by this auxiliary partial differential equation. If there was no polarization losses, it could simply be eliminated. It would just be the relative dielectric, and you would see we simply have Maxwell equation with a different dielectric. So the polarization model here is there to model frequency-independent losses. So we discretize this model in space, and we consider only one-dimensional propagation. So that means we're ignoring spreading losses and scattering losses. So whatever lossless parameters we estimate will be overestimations. So we discretize it, and we have to add perfectly matched layer boundary conditions to make sure we don't get spurious reflections from simulation boundaries, etc. And then we solve the system somewhat unusually as an initial value problem. So we initialize the electrical field to have that pulse shape that we actually measured in air in the simulation. And we give it a velocity of the speed of light in air towards the rock. And then we hit enter and let the simulation run, and we can produce a simulated response. We then twiddled with the parameters, which are the conductivity and the relaxation time tau, to match the observed result in terms of amplitude decay, arrival time, and somewhat more complicated shape. That's the spectral content. So we used the I norm rather than any sophisticated parameter fitting to come close. Anyways, the results were that if we consider the amplitude change from path 1 to 2, this can be explained by a resistivity of about 300 omega meters, and for the intermediate path 2500, and for the longest path 12 kilo ohm meters. And relaxation time that best matches the observed pulse shape change was about 0.4 nanoseconds. So if you know these parameters and you have a model, you can just compute the skin depth. It's a well-known formula in the purely conductive case, which is already a little bit complicated with square roots of square roots. Including the Debye model, it becomes real mess, so I just plotted here for the 1200 kilo ohm case. In the frequency range from about 50 kilohertz, which is below radar range, up to 65 megahertz, which is the largest frequency we have. And so you see that the black curve is pure conductivity losses, and the blue curve includes polarization losses. So you see that below 1 megahertz, the skin depth increases with decreasing frequency, which is good. But unfortunately, the dielectric constant, or the dielectric variable, I should say, also changes with frequency. And this means that we're in the dispersive regime, and the pulse sort of changes shape automatically, and that's not good for radar imaging. We're more into the EM model, stuff there. But in the radar range above 1 megahertz, the 3 megahertz component of our pulse seems to be dominated by conductivity losses, and the higher ones, 65 megahertz, is dominated by polarization losses. With these results in hand, we now turn to the second experiment, a reflection experiment. Let's So these results suggest that you could penetrate quite deep with the system through dry limestone. So we moved to a different location, which we knew to be 350 meters under the Pont d'Oreille River. So we aimed the antenna up through the ceiling, sent pulse up, and tried to measure the reflection from the water. Water is an excellent reflector, so this is that's why we chose the river. So since we have a model, we can try it in simulation too, which is fun. So I'll show you this this figure here. It's a video. From left to right, we have height, and 0 is where we're standing, 350 meters underground, and top, 350 meters, is where the river is. This is our dielectric model on the bottom, if I can get this arrow to disappear. I can use this one. This is the dielectric model. It hovers around 6 with some oscillations which mimic small irregularities in the rock formation. These generate clutter in the reflected signal, and here is a big peak of 80. That is the river. So this is the model, synthetic model. This is the electrical field, and it's 0 everywhere because we haven't turned the transmitter on, which I will do right now. So we'll see the pulse emerging, and it has all this high frequency stuff, but it's stripped off already. Right now it only has 20 megahertz and the 3 megahertz component. The 20 megahertz component doesn't really make it to the water. And here we have a reflection coming back, which we can track by eye, but of course in reality we're not Superman, we can't actually see this. All we can measure is the response here at ground 0, if you like. Anyways, we performed the experiments, and these are the results. I also show you the computed results from this model below for comparison. So we believe that this red stuff here, this red blip, is the actual reflection observed from the river. If you compare it to where it would be with the simulation, it's a little bit early, but in the simulation we used the electric value that was measured in a different location through dry limestone, so it could be a little bit off. It's also possible that the location of the water is not quite right, because we know where the bottom of the river is, but it could be in the river. The riverbed could be quite wet too. Actually, I don't know about this. So, but it seems that we see a reflection. To make sure we're not fooling ourselves into imagining stuff, we performed some other checks on the data. We looked at the correlation between the traces. You see in the top 500 traces stacked. We look at the correlation. If the correlation is high, we expect to see a signal, and if it's low, we expect to see noise, and it peaks right here at the correct place. There's other stuff here too, and I have no idea what it is. We don't know. Another thing you can look at is the dominant frequency content, weighted mean frequency, and it has a peak at the correct location of the correct value of 3. So we seem to indicate that this is actually the pulse you see. Of course, the only way to check is to get rid of the river and repeat, but I haven't figured out a way to do that. So to conclude, we believe that limestone is conductive near the walls, but resistive inside, and we hypothesize this is due to limited water penetration from the walls. If you look at the book values of limestone conductivity or resistivity, it varies from 100 to 100,000, 3 orders of magnitude for limestone, and we're sort of in the middle of that, from 300 to 12,000. So one may wonder why not just measure this conductivity from a borehole and validate this. But I believe that it's kind of hard to estimate conductivity without getting moisture contamination in the borehole. Borehole samples are contaminated with moisture, and I found a funny reference for this when I was doing some bedtime reading. I was reading the biography of Erwin Schrödinger, one of the founding fathers of quantum mechanics. Apparently in his PhD thesis he measured how conductivity of samples change when they're exposed to moist air. This was in 1910. Finally, we believe that we have detected the water target to 350 meters of rock. So in my remaining time, which is 30 seconds, I would like to mention the people who actually did most of the work, my co-authors, Joel Jansen from Tech Resources, and Michael Robinson, Colin Stowe, Gordon Stowe from Adrok. And I should also thank the staff at Ponderay mine in Washington for driving us around and keeping us safe. Thank you.
Are there any questions?
Ben Scriver, University of Arizona. I've seen many, many experiments like your limestone block experiments over many years, over 4 years. In all the experiments that I've seen, ultimately the conclusion was made that the actual signal that was being seen was going around the block of limestone. Many of the experiments are done in limestone.
Okay.
What is your argument that you're not seeing signals going around?
Yeah, I actually mentioned that, but probably too briefly. So what we did, okay, let's take path 4 as an example. So you're saying why what I'm measuring here didn't go through limestone and went around. Is that correct?
Yes.
Yeah, okay. So what we did, we measured the signal not just here, but at 10 locations to the left and 10 locations to the right. And then we compared amplitude. And we reasoned that if what you're saying is correct, then if we move this receiver more towards the left, the amplitude should go up since it's closer to the source. That did not happen. It went down. And that's the reason for believing it went through the limestone.
What's inside these drifts? Are they completely devoid of metal, or are they the usual kinds of metal or wires and ventilation?
I don't know. I just did the analysis. Maybe my colleague who is also here, Gordon, can answer it for you afterwards. I don't know.
My next question was about the reflection experiment of the river.
Yeah.
I was wondering what other things there were some distance down the drift that could also have reflected that signal.
We don't know. All I know is where the river is. Yeah.
Okay, please join me in thanking Case.